We're going to look at how ratios apply to real life. They can be used to solve real-world situations. In fact, I use them every now and then when I'm even watching the news. I get some partial data and I want to figure out what the full data would be. Let's look at this situation. Julia is planning to serve hors d'oeuvres at her wedding. Hors d'oeuvres are simply a fancy way of saying appetizers. She plans on offering 8 hors d'oeuvres for every 3 people. There's my ratio. 8 hors d'oeuvres for every 3 people. So I'm going to abbreviate hors d'oeuvres for 8 for every 3 people. If she has 240 people RSVP to the wedding, then how many hors d'oeuvres will she serve? Well, so we know that she's going to have 240 people there. We need to know how many hors d'oeuvres she has to have in order to make sure that everyone eats. So this is definitely real world. So I want you to think about this situation here. She's going to have 240 people. So when we think about that, we know that that's the total number of people that are going to be at her event. We've got 8 hors d'oeuvres for every 3 people, and there's going to be 240 people. So when we set up our ratio comparison here, we are going to use a set of 3 ratios. The first ratio is what I call the labeling ratio. This is the ratio that tells us what it is we're comparing, keeps us organized, and makes sure that we don't make a silly mistake. So we're going to compare the hors d'oeuvres to people. We have this small sample ratio of 8 hors d'oeuvres for every 3 people. This is what I call the given ratio. This is the ratio that they give us all of the information for. Okay, so we have 8 hors d'oeuvres, 3 people. This last ratio, this is the ratio where they are, is what I call the problem ratio, where they only give us one part of it and we have to solve for the other. Well, we know there's 240 people. So I keep all of my information regarding people down in the denominator of these ratios, so that way my work stays organized. You can't just put these numbers wherever you want, because once you have them all willy-nilly within your work, you're going to make a mistake. So the people information stays at the bottom. The hors d'oeuvres information is going to stay along the numerator, along the top, and that's going to keep me organized to make sure that I don't make a silly mistake. Now I just have to look at what we did earlier. I'm going to look at the multiplicative relationship from 3 to 240. And I'm going to ask myself, what is it that I would multiply 3 by in order to get 240? Well, that would be 80. And whatever I do to my denominator is what I'm going to do to my numerator. So I have to multiply 8 also times 80. And that gives me 640. So then my answer is, how many hors d'oeuvres do we need? We need 640 hors d'oeuvres. Let's look at another situation. Mrs. Hernandez was helping her students with their classroom economy bank accounts. The sum of the student with the most money and the student with the least money is $160. So I know this is going to be important. The ratio of the amount of students with the most money to the least money was 4 to 1. So our most to least is 4 to 1. How much money did they each have? Okay, well, the most plus the least is also $160, and I need to know how much they each had. This is similar to that summer berry punch problem that we looked at. And we looked at different types of ratios. We looked at having fruit punch to lemonade. We looked at fruit punch to total, lemonade to total. So we have to think about this problem here. And you can see they're giving us some totals. They're telling us the sum of their money was $160. So what this means is that since this problem is giving us some information that includes a total, I'm going to have to also include a total. So I'm going to use this small sample ratio that they gave me, and I'm going to find the total of it, which would be 5. 4 plus 1 is 5. So now what I have to do is take the information that it gives me, and I'm going to use 1. I'm going to pick the most. So for my labeling ratio this time, I'm going to do most to total. It wouldn't matter if I did least to total. This would still work. Then I know that my most is 4. Tells me right here. And my total is 5. So there's my given ratio. And then my problem ratio, again, is my total because it says most and least is 160. So now I'm going to solve for the amount of money that the student that has the most would have. So I'm going to look for this relationship, 5 to 160. Well, I know that's going to be that I'm multiplying by 32, so I have to multiply 4 by 32. Which gives me 128. So the student with the most money has $128. Now all I need to do to find the student with the least is subtract. The 160 minus 128 is going to leave me with $32. So the student with the least would have $32. I want to prove to you that it would not matter which one that I started with. Let's do the least to total. So it would be 1 to 5, and we know that this is 160. That relationship is going to be the same. It's going to be times 32. Well, 1 times 32 is 32. So I just proved that the person with the least has $32. No matter which ratio you would have started with, you would have been able to have found the least and the most. This problem is super important because you are going to have to read and sometimes understand the fact that you're going to need the total. Not all the time, but sometimes. So let's look at the next problem. It says, according to the 2010 census, the state of Oregon has a population of 40 people per square mile. This is a ratio, 40 people per square mile. The word per means for each. So there's 40 people for every square mile. So 40 people, oops, if I could spell, that would be good, per square mile. And I'm going to abbreviate square mile. If a county in Oregon measured 75 miles by 30 miles, then what is the population? So we know that we have one that's 75 miles by 30 miles, and we need to know what's the population. So this is going to require me to do some math up front. I am comparing in my ratio people and square miles. So that means I need 75 by 30 to give me square miles. So I'm going to have to multiply 75 by 30 to figure that out. So once I do this, I'm going to find out that it's going to be 2,250. So let's set up our proportion. We're comparing people to square miles. So we have 40 people per square mile. So 40 people for one square mile. We need to know how many people in 2,250 square miles. So clearly my relationship, I'm multiplying by 2,250. So let's work this through. Oops, what is it? 9. So we end up, I think I made a mistake in my multiplication. Let's start that over. So, whoops. I've got all my zeros here. 0, 20, 20. 8, 9, 10. So we're going to end up with 90,000 people. All right, I'm going to pause here. I want you to work this one out on your own. It is very similar to number 2. All right, so here I have worked the problem out both ways in case you chose Becca or Jenna to work with. But this is a total problem. It tells you that combined they sold a total of 385 boxes. So that means that you had to take that 8 and that 3 and put them together. Be very careful. Be on the lookout for those types of problems.